Right. So, okay, so by direct computation. Okay, so I'm going to do the mixed partials with respect to y and z, and I'll let you do the others. So, all right, so here's our h function. Let's write this down. It's xy cubed minus e to the yz plus z sine xy. Okay, so first let's take the partial of h with respect to y, and we get 3xy squared minus, now the partial with respect to y, z is treated as a constant here, so we're going to get z e to the yz. Okay. And then now we're taking the partial with respect to y, so we're treating that z as a constant, we're treating that x as a constant, and so we're going to get, since x is a constant, then when we use the chain rule, that x is going to pop out as a factor, and we're going to get zx cosine xy. Cool? All right. Now let's take the partial of h with respect to z instead. So we get 0. Partial with respect to z will give you minus y e to the yz. And now partial with respect to z of this, well, okay, lovely, no problem. I have z times what's a constant, and so the partial with respect to z of that is just that constant. It's sine of xy. So we're good so far. Okay. Okay, now we've got to take the mixed partials. So I'm going to take the z partial of this, and I'm going to get the y partial of that, and let's just see what happens. So, all right, I'm going to take the z partial of partial h with respect to y. Okay, z partial of all this stuff. So the z partial of that is 0. Oops. The z partial of this, now we've got to use the product rule because this is a function of z, that's got z's in it also. So I'm going to have two terms. First, putting the derivative there, the z partial of z is 1, and then I have e to the yz. Then I have z times, and now I got to take the z partial of this guy, the z partial of e to the yz, again, y is a constant, so I'm going to get y e to the yz. Is that okay? Okay. And now the z partial of this, again, you know, convenient, it's z times a bunch of stuff that's all constants, and so we have just x cosine of xy. Right. All right, so that was the z partial of this. Now let's take the y partial of this. And we get, okay, the y partial of 0 is still 0. That's good news. The y partial of this, okay, now, well, we gotta be careful here, right? Because this is, again, is a product rule problem. Y is a function of y, but so is e to the yz, also a function of y. So we're going to have minus. First, I'll take the y partial of y. That gives me 1, and then e to the yz. Now I've got plus y times, now I got to take the y partial of this guy, in which z is a constant that gets kicked out, so I get z e to the yz. And then the y partial of this, well, x is a constant, x gets kicked out, I get x cosine xy. And conveniently, these are exactly the same. That make sense?
Yeah.
Yeah, it's just, you got to be real careful when you're taking derivatives that, don't inadvertently set a variable equal to a constant. And so especially when you have the product rule coming up, like when you have something like this and you're taking a z partial of it, you're going to see the z and be like, oh, z times stuff. Okay, well, let's just call this a constant. But you can't. Yeah, exactly. Okay, and I'll let you do the others yourself, and it sounds like I think you're in good shape. Does anybody have any questions about this? All good?
So you say you have to expand the product rule before we did the constant, to like a constant.
I didn't quite understand. Say again?
So you said you have to do the product rule first and then take the partial with respect to z.
When you're taking the z partial of this guy right here, of this product, Yeah, you got to use the product rule. Yeah,
Oh,
that's right. That's all. I just used the product rule to turn this into, we've got two terms. One from taking the derivative of this times that. The other from taking this times the derivative of that.
okay.
Yeah. Yep. Okay. Let me stop this one.